real pole at the origin, and the other we have this complex pole, complex conjugate pole at minus 3 plus 4j minus 3 minus 4j. Okay, so since we know that the locus will start at the pole, we're going to have three loci altogether. But since we have no zero, all of the locus will end at infinity. Therefore, we need to find three asymptote lines. So the number of asymptote is going to be 3, which is number of pole minus number of zero. So we need to find the angle, the asymptote angle. It's going to be 3. It's going to be symmetrical about the real axis. So these are the asymptote angle: 60 degrees, 180, and 300 degrees. And then we need to also find the intersection of asymptote. All asymptote line will go through the intersection of asymptote, which is just summation of the pole minus summation of the zero. In this case, we don't have any zeros, divided by the number of pole minus the number of zero. So this is the asymptote line is going to intersect at -2. Since we have this complex pole, so you need to find the departure angle from the complex pole. All you have to do is just find one of them, and then it's going to be symmetrical about the real axis. Okay, so in that case, so we need to go to the before I explain the departure angle. Let's locate the pole and draw the asymptote line. Let's go to the diagram. Okay. So this is our three poles, one at the origin, and we have two complex poles. And then we have determined that since there's no zero, all locus will go to infinity. And therefore, we need to find three asymptote lines. So all asymptote intersect at -2. So we have computed asymptote line to go through -2. And then the first line at 60 degrees, and then you draw this blue line here is the first asymptote line. And then another line at 180, go all the way to the left. And then they are symmetrical about the real axis. And this is your third, going down at an angle of 300 degrees all the way down. So that is your asymptote line, three asymptote line. Okay, so now since we have this two complex pole, so okay, before that, on the real axis, locus exists to the left of odd number poles and zero. Since you only have one pole at the origin, so to the left of that pole, you're going to have you are going to have the locus. So all the way to the left of the pole at the origin, all the way to infinity, so you're going to have a locus. That's on the real axis. And then the locus is going to leave this complex pole. Therefore, we need to find the departure angle. So the departure angle is that the expression for departure angle is 180 minus the angle from other pole plus angle from other zeros. But since we don't have any zeros, all you have to do is find the angles from other pole. We have two other poles. Let's go down. Let's say we want to find the departure angle from the pole above the real axis. Now we have two other poles, one pole at the origin and one pole right underneath the complex pole. And of course, that angle is going to be 90 degrees from the complex pole. Another angle is you need to find the angle from the pole at the origin to the pole in question here. So this angle. So this is the pole that you want to find the departure angle. from the pole at the origin. So it's going to be slightly greater than 90 degrees. So you can compute that using arctangent, and then you can compute the angle. It's going to be 120 something. So this is your departure angle. Minus 90 here is from the complex pole, and minus 126.9 is from the pole at the origin. So you can compute that. So the departure angle is now negative 36.9 degrees. So it's going to leave the complex pole at an angle of negative 39 degrees going down. 0 degrees is to your right. But somehow this is going to turn and approach the asymptote line. So it is going to leave the complex pole at negative 36 degrees, and then it's going to turn around and approach the asymptote line. It's going to cross the imaginary axis. So where does the locus cross the imaginary axis? So we can determine that using the stability criterion. I cannot come to my mind. What is it? The Ruth table, the Ruth criterion, the Ruth stability criterion, because the value of K there is going to make the system marginally stable. So we can determine the point where the locus crossed the imaginary axis from the Ruth table. Okay, so we are done with the departure angle, and then we need to find the intersection with the imaginary axis. So we get the characteristic equation. Characteristic equation is just 1 plus the open loop transfer function equals 0. So this is the open loop transfer function. So and then you can now expand. This is going to be third order polynomial, and then now you develop the Ruth table, and then you can see that when K is equal to 150, the system becomes marginally stable. So you want to find the root when K is equal to 150. You can substitute back K is equal to 150 in the characteristic equation and find the roots. That's one way. That's what we have done before. So once we find the value of K that will make the system marginally stable, substitute that K back into the characteristic equation and solve for the roots, and then we are going to get the intersection with the imaginary axis. But today we are going to use this auxiliary equation. So the equation just above, where the value of K will make system marginally stable, which is the element in the first column equals 0. So we can directly use the equation above, the element in the first column equals 0 to be our auxiliary equation to compute for the intersection of imaginary axis. So we're going to have 6s squared plus K is going to be equal to 0. Then we can solve that for intersection of imaginary axis. So you can either substitute K is equal to 150 in the characteristic equation and solve for the roots. So this is where the intersection of imaginary axis, which is 5j and negative 5j, by substituting K equal 150 in the characteristic equation and solve for the roots. That's one way. Another way is to use this auxiliary equation. So when you use the auxiliary equation, you have this 6s squared plus 150. So you just use the equation just above the first element in the first column equals 0. So this is going to be 6s squared plus K equals 0. Then you can easily solve for intersection with imaginary axis. So you get this negative plus and minus 5j. So either way, you just choose whatever method that is convenient to you. Sometimes it is not that easy to find the roots of the higher order polynomial, so it's just helpful. It is much easier to use this auxiliary equation to solve for this intersection with imaginary axis. So either way, you're going to get plus and minus 5j. Now you can now so this is now 5j and this is minus 5j. So this is the intersection of imaginary axis, and then now you can now draw your Locus diagram to a reasonable degree of accuracy. And take note that your Locus diagram is always symmetrical about the real axis. Okay, so that's it. That's just so in this case there is no breakaway or breaking point. Okay, the step 8, I guess, because on the real axis, the locus is not leaving. It's not going out of the, because it is going all the way to infinity along the asymptote. So in this example, you can skip the step where you need to find the breakaway point or the breaking point. So that's it for this example. By the way, I have uploaded your third assignment to your e-learning. You can start working on your assignment, which is about this stability of control system and drawing the Locus diagram, and as well as interpretation of the Locus diagram. Okay. After all that, after all that, what do we get out of this? We took so much trouble to learn how to draw this root locus diagram. What actually do we get out of it? Okay, so this is the next topic of discussion. But before we go there, is there any question that you want to ask? You can type your question in the chat box, or you can unmute yourself and ask your question verbally. Can you repeat on the departure angle, the departure angle? All right. Okay, so this, let's go back to example 315. Example 315. So you have these two complex poles at -1 plus j, -1, -j. Once you have a complex pole, because the locus start at the pole, so you need to know the departure angle. Does it go to the left, to the right, to up or down? So in this case, so you have these two complex poles. You just need to find the departure angle from one of them, because the other one is going to be symmetrical. Let's say now you want to find the departure angle from the pole above the complex pole above the real axis. So you need to find the angle from other pole and 0. So you have two other poles and one more 0. So this is the angle from the pole at the origin is in this example 135. The angle from the other complex pole is 90, and the angle from other 0 is 45 degrees. So the departure angle is computed by 180 minus summation of theta p and theta z. Here you have two theta p, 135 and 90. So minus 135 minus 90, but you have 0 here. So it plus 45 degrees. So this is now you get the departure angle of you get the departure angle of 0 degrees. 0 degrees meaning that you go straight to your right. That's 0 degrees. But in example that we discussed today, we don't have this 0. We have no 0. We only have 3 poles. So all you have to compute is this theta p1 and theta p2. So theta p2 is 90 degrees, but today theta P1 here is not 135. Okay, so this is the angle that you, the angle from the complex pole, this is 90 degrees. You draw a line, straight line, and connecting the two poles, and you measure the angle from your right, from parallel to the real axis. So that's 90 degrees. And then you draw another line connecting the pole that you want to find the departure angle of to the pole at the origin. And this is the angle. You measure the angle from the line parallel to the real axis. So that's 90 degrees. That's another 29 degrees. So this is one, that's another 30, I think 39 degrees. So this is 129. Okay, so 126. So 180 minus 126. So this is the angle from the pole at the origin. So minus 90 here is from the complex pole below the real axis. You don't have no zero, so you don't have theta z here, and then you just compute 180 minus 126.9 minus 90, so you get now the departure angle of 36.9 degrees. Any other question? Yeah, 129. All right, you just draw this angle, and this is 90, right? This is 90. So you need to add another angle of arc tangent of 3 divided by 4, yes? 3 divided by 4. Arc tangent of 3 divided by 4. You're going to get 36.9 degrees, 36.9 degrees plus 90, so 126.9. 126.9 degrees is the angle from the pole at the origin to the angle that you want to find the departure angle of. So when you compute that, you get the departure angle of negative 36.9. You can try and measure that angle. If you have a protractor, then you can measure this angle. Any other question? Okay, so after all the pain that we have gone through, what do we get out of this? Our main objective is to design the controller K. Interpretation of root locus 2. Interpretation of root locus and controller design. So this is the topic that we want to discuss today. How do we interpret the behavior of the system? Behavior meaning the time response of the system based on the root locus diagram, and how can we select the value of the controller K to meet certain specification. Okay? When the design of a feedback control system is undertaken, the controller must be chosen such that the closed loop system is stable. So we want the location of the roots to be on the left of the imaginary axis for it to be stable. And the transient response is satisfactory, that all specifications are satisfied. How can we choose the value of K, which is the controller gain, so that all these criteria can be met? For a stable system, all roots must lie on the left-hand side of the imaginary axis. We don't want to choose the value of K such that the root is on the right-hand side of the imaginary axis. That is for sure. But how can we determine the damping ratio, natural frequency, the damped natural frequency, the time constant just from the root locus diagram? We can estimate all these values from the root locus diagram. See, the value of this parameter can be estimated from the location of the dominant roots from the root locus in the S-plane. We are just going to estimate the behavior of the system based on the dominant roots. So what are the dominant roots? The dominant roots are the roots which is closer to the imaginary axis. Okay, so I have written some explanation again here. Yeah. So imagine that this is our block diagram. So G of S is the system to be controlled. H of S is the feedback transfer function, and K is the proportional controller gain. We want to choose the value of K such that it will meet some specification. Okay, so the root locus diagram gives the location of the roots for all K from 0 to infinity. So we know that the roots is going to be for any value of K from 0 to infinity, the root is going to be located on the locus. So that is one thing that we already know. For any value of K from 0 to infinity. So when the value of K is selected, when we select a value of K, and then we are going to have all the roots already determined on the S-plane for a particular value of K. So how do we evaluate the time constant, the damping ratio, the natural frequency, the damped natural frequency from the location of the roots? So let's say for example, then for a selected value of K, let's say we selected a value of K, just randomly select a value of K equal 5 or equal 6 or equal 10. For that particular value of K, we are going to have the location of the roots. Okay? For if we have third order system, we are going to have 3 roots. If this is fourth order system, we're going to have 4 roots. If we have fifth order system, we're going to have 5 roots. So the little square here is the possible location of the roots for a selected value of the gain K. So we are going to estimate the behavior of the system just based on the dominant roots. So which are, okay, now, for example, now we have this a fifth order system. You have these 5 roots, 1, 2, 3 on the far right. For 5, you have 5 roots. So the dominant root is the dominant roots are the roots closer to the imaginary axis. The further away the roots from the imaginary axis, the roots now become non-dominant. The time constant for this root is become very, very large. No, the time constant for this root become very, very small. So it's going to die out very quickly. So the behavior of the system is going to be dictated by the roots closer to the imaginary axis. In this case, we are going to estimate the behavior of the system using the second order system. Now we are just left the dominant root here. We only have two dominant roots. We are going to estimate the behavior of the system using the second order system. For that case, we need to go back to chapter 2 when we discuss about the time constant for when we discuss the time response of a second order system. Okay, so let me go back and select our notes that's discussed about second order system. Hopefully that I can find the correct notes. Sometime wait for, I guess this one, wait for a second. Okay, so this is our second order system. If you look back, see, this is the second order system. The denominator is written s squared plus 2 zeta omega ns plus omega n squared. So the roots of this quadratic equation, we already know that. So this is the roots. Negative zeta omega n plus and minus omega n squared of zeta squared minus 1. But for complex root, when zeta is less than 1, so this is going to become a complex number. We are not interested in zeta greater than 1. For damping ratio less than 1, this is going to be a complex part of the roots. So the real part of the root is minus zeta omega n. the imaginary part of the root is omega n 1 minus zeta squared. See, from this second order transfer function. So this is the root. And if you look at the response, so this is the response. This zeta e raised to the power of zeta omega nt. So this tells us about the time constant of the system. So the time constant of the system is 1 divided by zeta omega n. So there's a time constant. So this is the omega d. The damped natural frequency is just the actual frequency of oscillation is omega d, omega n 1 minus zeta squared. So this is the real part of the root, and omega d is the imaginary part of the root. How convenient is that? And zeta here, we can compute the zeta from the ratio of this, the real part of the roots as well as the imaginary part of the roots. Now let's go back to the interpretation of root locus diagram. All right. So the roots that is further away from the imaginary axis, we call that non-dominant. And let's forget about the roots is far away from the imaginary axis. Just focus our attention to these two roots. So the real part of the root is negative zeta omega n. From here, we can get the time constant. 1 over that, 1 over zeta omega n, 1 over the real part of the roots, we are going to get the time constant. So the further away you are, the time constant is going to become smaller and smaller. That is why the root that is further away is called the non-dominant root. When you move closer to the imaginary axis, you're going to have a significant value of the time constant. And the imaginary part of your roots is known as the omega d, the damped natural frequency, which is omega n minus 1, omega n squared over 1 minus zeta squared, the imaginary part of the roots. And the distance from the origin to our roots, you can conveniently use the Pythagoras theorem. You can do this, okay? Pythagoras theorem. You can compute the distance from the origin to the selected root. It's going to be just the natural frequency. And this angle beta here will now will now relate to our damping ratio. See, you can use the tangent or the cosine. It is just trigonometric function here. The triangle there, you can get the relationship between beta omega n with the imaginary part of the roots as well as the real part of the roots. So the damping ratio is just the cosine of that angle. So that's a damping ratio. Damping ratio is just the cosine of that angle beta. The time constant is 1 over the real part of the root. The damped natural frequency is just the real part of the root. The natural frequency is the distance of the roots to the origin. So that is how we interpret the root locus diagram. With all that information, we can now select the value of k given some specification. Let's say the specifications say that select the value of k such that the time constant is less than 1 second, for example. Therefore, you know that you should not go to the left of a vertical line where the real part of the root is equal to 1, something like that. And for example, if the specification is given in terms of damping ratio, let's say damping ratio, the specifications say the damping ratio must be less than 0.5, for example. Then you need to measure the angle, and then you should you should not go below that line. See, the closer you are to the imaginary axis, the bigger your time constant. So the bigger the value of your beta here, let me guess, cosine beta, the smaller the damping ratio becomes. So there's an inverse relationship between zeta and beta. Okay, so that is how you interpret the Locus diagram. I know there's a lot to process. Never mind. When we look at an example, then everything is going to be clear. So I guess let's take a break. Yeah, let's take a break. Let's take a break and then come back here at 5, and we will continue our discussion. Okay, so let's take a break and come back here at 5. If you can hear my voice and see my screen, please type yes in the chat box. Okay, so thank you very much. Let us continue our discussion. So we have talked about how we can interpret the behavior of the system. We can approximate the behavior of the system. Behavior meaning that the time response of the system based on the dominant roots. The dominant roots are the roots which is closer to the imaginary axis. So it is going to become clearer when we go through example. Okay, let's go through example. See, we are given a control system. A control system is represented by a block diagram shown below. So we have this third order control system with a unity feedback and a proportional controller P, K, just again K. The question has two parts. One is draw the Locus diagram when K increases from 0 to infinity. That's the first part. And the second part is probably the design part. In this case, it's not actually design. The value of K is selected for you. It is given that when K is equal to 10, the roots of the characteristic equation are -3, -1, plus and minus 2.2 for J. Sometimes the roots are not given, but in this case, it is called the user-friendly, the student-friendly question. Sometimes the roots are given. And then it wants to the question wants us to determine the damping ratio, natural frequency, time constant for K is equal to 10 for the selected value of K is equal to 10. So this is a typical question that you're going to encounter in your test or in your final exam. The first part is given a control system, the first part is to draw the Locus diagram. Normally you can earn 6 marks out of that. And the second part of the question, which is interpretation of the Locus diagram, will give you another 4 marks. Okay, so the first part is draw the Locus diagram, and then the second part is answer whatever question necessary. So let's go through my notes. Okay, again, so draw the Locus diagram. Is it the same? Is it the same question? Let me double check. S square, yeah, it's the same question. All right. First, we need to draw the Locus diagram, and then we need to if the value of controller gain k is selected to be 10, what are the value of this quantity that will determine the response of the system? The damping ratio, natural frequency damp, natural frequency, as well as the time constant. So remember that this is the critical part. The first step is always the critical part. So you draw the locus diagram from the open loop transfer function. Do not obtain the closed loop transfer function, which is y divided by u, using the g divided by 1 plus gh. No, you need to extract the open loop transfer function. That is the first mistake that some of you is going to make. So you are given this closed loop system. To draw the locus diagram, your first task is to get the open loop transfer function, which is just the loop gain. Okay, so this is now the open loop transfer function. And then you go through all the 9 steps of drawing the locus diagram. So here we're going to have 3 poles. We don't have any zeros. Compute the asymptote angle, compute the intersection of asymptote, compute the intersection with imaginary axis, and then compute the departure angle. So with all this information, you can now easily draw with reasonable degree of accuracy your locus diagram. You have everything now. It's so easy with all the points. So let's go to the drawing. So there's your 3 poles. To the left, you only have 1 pole on the real axis. So to the left of the real axis, you have this locus, and intersection with the imaginary axis happen at plus and minus 3.4j. So that's 3.4j for you. So the departure angle at negative 45 degrees. So it goes to negative 45 and turn back, and then that is your locus diagram. So this is your asymptote line, intersect at negative 1.6. So this is 1.6, 60 degrees. That's one of your asymptote angle. And now you can now draw your locus diagram. That's the first part. It's going to get you 6 marks. I'm expecting all of you should get that 6 marks. This is just, everything is there. There's nothing to it. We have gone through so many examples already. Now the second part. So the second part is the interpretation of the locus diagram. So the question wants us to find all these quantities: damping ratio, natural frequency, damp, natural frequency, and time constant, if the proportionality constant k is selected to be 10. So now all you have to do is take this 10, substitute in the characteristic equation, and obtain what the roots are. But here it is given. See, the roots are already given. But in case the roots are not given, so it is just given the value of k equal to 10. The roots are not given. You need to find that. So take this value of k equal to 10, substitute in the characteristic equation. So k is, what the hell is this? Why? Okay, this is a mistake there. Not k is equal to 0, k should be equal to 10. K is selected to be 10. So make a correction. Make a correction. There's a mistake there. So k is equal to 10, 10 plus 8 is 18. So the characteristic equation is correct. And now you can now find the roots, which is -3, -1 plus 2.24j, which is the same thing as given in the question. Sometimes the roots are not given, sometimes the roots are given. If it is not given, then you need to compute using the characteristic equation. Substitute the value of k, And then now you get the roots. Now this is now the dominant roots, which is closer to the origin. So -3 is further. Let's go back to the block diagram. So when the value of k is equal to 10, you have three roots, one at -3. So this is the real root, and we have two complex root at -1 plus 2.24j. That's one of them, -1 plus 2.24j, and then there's another one, -1 to -2.24j. The roots must be on the locus. See, it must be on the red line. If you don't get on the red line, meaning that there's something wrong with your computation. So you have three. For the value of k is equal to 10, you're going to have 3 roots, which should be on the locus. How do you get all this damping ratio, natural frequency, time constant from the roots? So we just estimate those quantities from the dominant root. This is the non-dominant root, so just ignore that. The time constant is just 1 over the real part of the root. So 1 over the real part of the imaginary roots of the complex root. The real part of the complex root is 1. So the time constant, it should be 1. The imaginary part is the damped natural frequency. Okay, so here, all right. So this is the location of the dominant roots at -1, 2.24j. So 1 over 1 will give you the time constant. So time constant is 1 over the real part of the root, which is 1 second. The real part of the root is 1. The damped natural frequency is just the imaginary part of the root. So 2.24 will give you the 2.24 is the damped natural frequency. The natural frequency is the distance from the roots to the origin. So you can use the Pythagoras theorem, which is square root of 1 square plus 2.24 square. So that is your natural frequency. The damping ratio, we can compute the damping ratio based on that angle beta. First, you compute the angle beta, or you can measure the angle beta. You can use the arctangent. So the angle beta is 65.9 degrees, and then the cosine of that is the damping ratio. So this is now, you can now extract for k is equal to 10. When k is equal to 10, you can extract all this information from the root locus diagram. And this quantity will dictate how your system behaves. So back in chapter 2, we already discussed the time response of second order control system based on all these quantities. So all you have to do is find the real part of the roots. 1 over that is going to give you the time constant. The real part of the root, the imaginary part of the roots will give you the damped natural frequency. The cosine of that angle is going to give you the damping ratio. Okay, so any question? All right. That is the first type of question that you may encounter in your exam. So here I call this a student-friendly question, because the value of k is selected for you. All you have to do is obtain all these quantities. The second type of question that you may encounter is you will be asked to determine the value of k when the value of this damping ratio time constant is given. So that is a more difficult question. Given specification, let's say for example, time constant must be 0.5 second, and what is the value of k? So that is the second type of question that you might or you will encounter in your exam or test, which is in our second example. In second example, example 3.18. For a control system shown below, choose so this is nasty question. Choose the value of k such that the maximum value of damping ratio is 0.5 and the minimum value of time constant is 1 second. I think there's a mistake there. Minimum, okay, there's a mistake in the question. Okay, here is the correct question. Choose or select the value of k such that the maximum damping ratio is 0.5 and the maximum value of time constant is 1 second. So both is maximum. So the minimum here should be maximum. Both maximum. All right, so let's go to my notes. So this is a correct question. Select or choose the value of controller gain k so that it will meet the specification. You are given the specification of time constant must be less than time constant must be less than 1 second, and the damping ratio must be less than 0.5. And of course, your first task is to draw the Locus diagram. The Locus diagram you draw using the open loop transfer function. Get the open loop transfer function. Do not extract the closed loop transfer function. Okay, so just the loop gain. So this is now your open loop transfer function. Now put that in a zero pole format, and now identify your poles. You have 3 poles, one at the origin, one at -4, one at -10. You have no zeros. Asymptote angle. Again, in fact, you don't have to compute asymptote angle. It is going to be the same. If you have 3 asymptote angle is going to be 60, 180, 300. Intersection of asymptote. In this case, you're going to have a breakaway point. So breakaway point at -1.76, intersection with imaginary axis at 6.32J. So all this value is computed using the 9th step of root locus diagram. With all this information, now you can draw the locus diagram. That will give you 6 marks. Okay, so let us draw that. How do I rotate this? How do I rotate this? Oh no. It is, you can either tilt, rotate. No. How do I rotate this? There must be a button somewhere, right? Yeah, I can rotate this. Or you can tilt. You can tilt your head to your left. Okay, everybody now tilt your head to the left. Okay. All right. So now this is, you have 3 poles, one at the origin. Tilt your head to the left. One at the origin, one at -4, and one at -10. Press Control Alternate and plus at the same time. Let me do that. Control Alternate plus. Control Alternate plus. It's not happening. No, it's not happening. Well, Oh shit. Sucks. What the hell's going on? I tell you what. Control Shift plus. Control Shift plus. There you go. Okay, all right. There you go. Okay, Control Shift plus. Yay. All right. No, everything is rotated. What the hell? Oh, okay. No, I'm not comfortable. I am just not comfortable discussing this. Control Shift minus. Control Shift minus. Anyway, we are no. This is too much to imagine, too much information for you to digest. To digest here. Oh, okay, so I have a solution here. I have a solution. Don't worry about it. I have a solution. So we are going to end our class here today. I'm going to rescan my notes so that it's going to be vertical. Okay, so let us just take a break here, and we'll come back tomorrow and we discuss this. And by the way, we are ahead of our syllabus. And this is too much for you to imagine. Even I cannot see those information here. All right, so we are going to take a break here. We're going to end the class here. If you have any question, then you can type your question in the chat box, at least for the previous example. And then we are going to take a break. We're going to end our class here today. I'll try to rescan and reorientate this diagram. And then we have the discussion tomorrow. No, this is too much. This is too much. All right. So that's the end of today, I guess.